Okay, this is my solution for the problem that we did on buoyancy. And what we did was we had a 1 kilogram mass submerged in water. And we were measuring the tension in a rod required to keep it from sinking. So we had a scale attached to that rod, and the scale reads that the tension in the rod is 8.5 newtons. Now, this was how we discovered that there is a buoyant force, but really how you want to do this problem is you want to start the same way we do all force problems, with a free body diagram. So in the free body diagram, there's two forces, apparently. There's the tension in the rod, and there's the force of gravity, mg. But I realize now that for a 1 kilogram, that should have been 10 newtons. So there must actually be a third force. There must be this force, and you could call it, a question force, or with a little bit of foresight, you could call it the buoyant force. Okay, and so we choose axes. I'm going to choose the upward being positive, and we write that the sum of the forces is equal to the force of tension plus the buoyant force minus mg. And because it's in equilibrium and it's not accelerating, this is just 0. Okay, so that means that the force of tension, 8.5 newtons, plus the buoyant force minus the force of gravity, which is 10 newtons, is equal to 0. So the buoyant force must be 1.5 newtons. So what does this mean? Well, what it means is that before we had this thing submerged, there was an equal volume of water. And so that water wasn't moving anywhere either, and so there must have been a buoyant force on that piece too. And in that case, the buoyant force would be simply balancing out the gravity on water. And so what we realize is that the buoyant force has to be equal to the weight of the water displaced. In other words, it has to be equal to the water that is the same volume as the thing that's submerged. Okay, so that means it's the density of water times the volume of the mass times g. And so that means that the volume of the thing that's submerged is the buoyant force divided by the density of water and g. So we have 1.5 newtons divided by the density of water, which is 1,000 kilograms per cubic meter, times 10 meters per second squared, which is 1.5 times 10 to the, let's see, 1, 2, 3, 4, minus 4, and we'll have that in meters cubed. Cubic meters a lot, of course, and so if we want to convert that into centimeters, let's see, there's 10 to the 2 centimeters in 1 meter, so 10 to the 6 centimeters in cubic centimeters in a cubic meter, so that means it's 150 cubic centimeters. And we verified that that's true. Okay.